were here, both co-chair, Professor Gelfand, and myself, Dimitri Solmatin of HE Delft. And it's my pleasure to announce the next lecture from Professor Sivapalan. He is a very well-known hydrologist, scientist, and even philosopher of science, with the recipient of many prizes, author of many papers highly cited, and the person who contributed to development in hydrology in the last decades considerably, very considerably. So, Professor Sivapalan, floor is yours. It is 45 minutes lecture, 15 minutes for questions. Thank you very much for attending this school at such an early hour in Illinois. Thank you for waking up so early. And thank you for being with us.
All right. Good afternoon. Good evening, everyone, wherever you are in Europe or Asia. It's a pleasure for me to give this lecture. I guess thanks to COVID-19, technology has advanced, and now we're able to give this lecture through Zoom and address participants from all over the world. So I'm really pleased to give this lecture, and I hope that you've enjoyed the lectures so far, and you're patient enough to listen to me for the next 1 hour. As Professor Solmatin said, my talk will be a little bit more philosophical. Hope that you are a little bit more patient to listen to my talk, and I will be going a little bit fast because I packed too much into my presentation, but I already circulated a couple of papers from which this paper was drawn. So even if you miss something from my talk, you should be able to find more information in the paper that I will cite. Thank you very much. So let me just go to my talk. Is that okay?
Yes, sure. So
okay.
If you could click share screen and choose PowerPoint,
yeah,
then you'll be on air.
Okay. Great. Thank you very much. So my talk today presents a more personal perspective on the growth of hydrological understanding over the last 50 years, with a particular focus on hydrological modeling and predictions. So as I mentioned earlier, the talk that I'm giving is drawn from 2 papers that were published in the last 3-4 years. And the organizers of this lecture have these papers, so if you're interested, you can easily find them from them, or ask for them, or you can find them in the journals. So in 2017, in one of the papers that I cited, we looked at the growth of hydrology or hydrologic understanding over the last century, and we argued that this over the last century there has been a lot of growth in hydrological understanding, but this understanding did not grow gradually. It went through spurts of growth and stagnation, and we decided to break down into 5 different eras, as you can see in this figure. Now, when I was an undergraduate student in 1972, when I started my education of hydrology, hydrology was taught to me in just 10 lectures. And there were 3 things that were covered in the 10 lectures. And each of them covered 3 of the earlier eras in hydrology, the growth of hydrology. The first topic was flood frequency analysis, which belonged to the empirical era. The second topic was runoff generation, or what we call the curve number method of estimating runoff generation. That belonged to what we called the rationalization era, 1930s to 1950. you know, Robert Horton, father of American hydrology, was heavily involved in this period. And the third pillar of hydrology that I learned as an undergraduate was the so-called unit hydrograph method that belonged to what we call the systems era. So those are the three things that I learned as an undergraduate. I still remember the frustration I felt as a civil engineering undergraduate student, the frustration of the total disconnect to fluid mechanics that I was also learning at the same time. So the focus in hydrology at the time was on lumped empirical methods, and I was frustrated, but I was also intrigued that simple approaches like that even worked. And clearly, the same frustration I was feeling was felt by many other hydrologists, more eminent hydrologists, and this frustration ultimately led to what we call the process era. And Alan Fries from Canada was the pioneer in this area. And so the process, in the process era, they basically applied fluid mechanics principles, I would say Newtonian mechanics, to finally address prediction problems in hydrology. So this is an example of the kind of approach that was presented in 1969 in the Fries and Harland paper. So you basically break down the catchment into smaller components, and you applied hydrodynamic theories of flow over land and flow in subsurface, and you put them together and to build models. Now, this approach was presented, but it was slow to take off because of several problems. I would mention three problems that were involved. One is when you break down the catchment and you want to apply these governing equations, where do you go for parameters? Because it needed a lot of information, and we were not ready to have all this information available to us. That was one problem. The second problem was computing power. The computers of those days were able to be applied only for simple hypothetical catchments, and it was harder to take it to much larger catchments. So that was the second problem. So much of the progress in this area was limited to small catchments, and the approach was bedeviled by parameter estimation problems and so on. Now I think I should mention that we have overcome some of these problems. We have much more powerful computers and much more information becoming available about landscape properties. And now people are building more and more complex models and expanding to larger and larger catchments, even leading to the ambition to model the entire world at the resolution of 30 meters. So this is now making a lot of progress. We are making a lot of progress in this area, and more and more these kinds of models are becoming necessary to address problems of climate change. So that's a motivation for what we call the geoscience era that started in the 1990s. But there was one problem that remained. That problem I would call the scale problem. That the governing equations, based on Newtonian mechanics, hydrodynamics, assumed they divided the landscape into rectangular or triangular finite elements. They assumed the property to be uniform within these elements, but clearly there's a lot more heterogeneity than could be handled in these models. As you can see in this picture, there's a lot of heterogeneity at all scales. Okay, so how do you deal with heterogeneity was a major problem. I would call it the scale problem, and the problem is this heterogeneity doesn't go away even if you go down to 1 meter scale. Even at 1 meter scale, there's heterogeneity. So the idea is that you cannot keep on going smaller and smaller and smaller and hope that the world will become uniform, because it will not. So that was a major problem that is still causing a lot of trouble for physically based rainfall runoff modeling. And but there's a way forward, and the positive thing, or the silver lining, if you might say, is that in spite of this heterogeneity is not totally random. There is organization. That if you look at different scales, different aspects, different features of the landscape dominated the heterogeneity. So there's organization. And the question is, can we utilize this organization to build models that are physically based? So that was a challenge. And that was about the time that I started my own PhD. So my PhD was focused on these scale problems. So one of the things that we did as part of my PhD and my postdoc work was to ask the question whether there exists any kind of scale below which you don't have to go. That there's a scale that we can use as a building block, and any variability, heterogeneity that exists at larger scales can be explicitly resolved. Any heterogeneity that's below that scale, we can parameterize the effects of that, and therefore build physically based models that do not require a lot of information at small scales. That was the hope. And so during my PhD, I did this analysis and came to this idea that, yes, it does exist a scale like that, and we called it the representative elementary area. During my work, if we claimed that it was about 1 square kilometer, later people have come around and saying that, yeah, it may be 2 square kilometers, 3 square kilometers, but nevertheless, there's some support for the idea that there's a scale at below which you don't have to go. And the question is now, can we now reorganize the physically based approach to modeling, building on that idea? So that was the work of one of my PhD students, Paolo Reggiani. So he took this idea further and divided up large catchments into sub-catchments. He called it representative elementary watersheds. And he wrote down from first principles balance equations for mass, momentum, energy, and entropy, and so on, and developed a constitutive theory to support the governing equations coming from this, to make them fully determinate. So that was something that Paolo Reggiani did as part of his PhD. So I would summarize the approach that we have adopted all the way from Alfred's work to what Paolo Reggiani did. I would call it the upward approach to modeling. So starting from first principles, integrate up to the scale that you are interested in, and then build models on the basis of these building blocks. This is called the upward approach that Wegener called. Now, this approach, to make it practical, you still have to do a lot more work. You know, I mentioned about the heterogeneity, the subgrid heterogeneity. Somehow the effects of this subgrid heterogeneity has to be parameterized, how it impacts on the exchange fluxes from one REW to another REW, or from one region within an REW to another region. For example, from shallow unsubsaturated zone to the surface, or saturated zone to the unsaturated zone, and so on. So all of these have to be parameterized, the effect of heterogeneity be parameterized, and that is not an easy thing to do. That also slowed down the work. But nevertheless, we did some early work on this, and we built prototype models that could handle this. So a Korean student of mine in Australia developed a prototype model which he called the CREW model. And this is I'm just presenting this slide to tell you an example of how we built the closure relationships for the exchange fluxes. And this is an example of the result. So basically, after you do all of these things, for every REW, you come up with balance equations, mass balance equations for various compartments of a representative elementary watershed. So these are like water balance equations for the unsaturated zone, for the saturated zone, and so on, for the channel zone, and so on. So, and then you basically have coupled equations, coupled ordinary differential equations, and then you solve them using any kind of numerical model, numerical scheme. And another prototype model that was built on the basis of same ideas was a colleague of mine in China, he developed a model building on the work of my Korean student. We call it the through model. And we then applied this model in 2009 to a couple of catchments in the United States. Basically, we divided the large catchment into a large number of smaller sub-catchments, and we collected parameter values and built constitutive relationships, built closure relationships, and then applied the model. This is an example of the application. The model was able to produce spatially heterogeneous runoff generation, like subsurface flow and saturation excess runoff and overland saturation excess overland flow and infiltration excess overland flow and so on. And these are examples of the output of this model, of the through model based on the upward approach that I explained to you. Okay, so that is so far what I've covered so far is I started with the empirical approach, the frustration of the empirical approach, and then the attempts that we made to build models based on the Newtonian upward approach. And I put this slide back just to remind you that the ultimate result of this upscaling was balance equation for water balance for various compartments of a catchment. But they may look very complicated, but in reality, these equations that I'm presenting to you are no different to the kind of equation that you might find in a standard, what we call a conceptual model. You remember, models like the Stanford watershed model, or the Wick model, or the HPV model. All of these models are called conceptual. They come up with balance equations exactly like these a priori, and then they apply these models and calibrate and so on. And so the outcome of the upward approach based on the hydrodynamics is no different to what you might actually see in a conceptual model. So I just want to move on to the conceptual model a little bit. Now, when I moved to Australia in 1988, I started developing a conceptual model myself. It was called LASCAM. I used the model development as a way of learning about hydrology in Western Australia. So this LASCAM model is very similar to the HPV model, which is very popular in Europe. So I developed this model for West Australian conditions. And here are some examples of the output of this model. So, if you visually, the model does a very good job in mimicking the observed hydrograph in a year or over multiple years. And but they were after doing this and after being very happy about building this model, there was a problem. I came up with a challenge, and the challenge was that in the LASCAM model, as in any other model, conceptual model, being in Western Australia, 95% of the water balance was evaporation. So of the 20 parameters in the model, 6 parameters were devoted to making sure that we were mimicking the evaporation well, evapotranspiration. 6 parameters. And I needed 6 parameters. Now, one of my PhD students, Richard Silverstein, towards the end of this work, went and did a field experiment in the West Australian forest. And he came up with a conclusion after extensive work on the left side of this slide. He did this work in Western Australia, and I was shocked to find, on the right-hand side, I'm sorry. I was shocked to find that he did this experiment in two week periods, one in the summer and one in the winter, under very wet conditions, under very dry conditions. And shocking for me was that he found that the actual evaporation rate, daily evaporation rate, was 2.5 millimeters per day during the winter and 2.5 millimeters per day during summer every day. So it was shocking because if it is that simple, if it's only 2.5 millimeters per day, why do you need a model? Why do you need 6 parameters? So that was a shock to my system. And the reason, I can tell you the reason for this is because West Australian trees, the eucalyptus trees, they have the ability to send roots down all the way to the water table at 35 meters below the surface. And so whenever there's not enough rain, and 6 months of the year there's no rain, they are able to tap into groundwater. And so they kept on transpiring as if there was no water shortage. But I put I put so much emphasis on how trees adapt to dry conditions. All of that it was not needed because the trees have adapted to the environment there. So that was a simplicity that the trees produced that my model was not able to handle. Same story on the left-hand side in Northern Territory in Australia, Northern Australia. There, the trees have a different adaptation strategy. So when there was a lot of water available, they would transpire a lot, but there was also an understory. The understory, meaning grasses, they transpired at the rate of 3 millimeters per day, as opposed to trees which transpired at 1 millimeter per day. But during the dry period, the trees continued to transpire 1 millimeter per day, but the grasses died. So that was an adaptation strategy in Northern Territory. So these two aspects, how the vegetation adapted differently in different places, a Newtonian approach couldn't handle. So in other words, we need to, our Newtonian approach, the hydrodynamic approach had limitations because it cannot handle how the vegetation handles evaporation. So round about this time, I had a visitor from Germany, Hartmut Wittenberg. He came and spent 6 months with me and introduced me to a new way of modeling. So what he did is that he analyzed Western Australian catchments, which was strongly impacted by seasonality, Mediterranean type seasonality. And all he did was analyze stream flow recessions. The stream flow decline after the rainfall stopped. He analyzed these recessions very, very carefully over the entire year and fitted relationship between established relationship between storage and discharge. And he found that the parameters of that relationship varied seasonally. And he attributed that seasonality of the parameters to seasonality of potential evaporation. And on the basis of that alone, he built a simple water balance model to mimic the groundwater flow. And that was very successful. So that introduced me to the idea that we can build models based on learning from data, data-based models. So that gave me an idea. And then I went further than what he did and had a whole group of students coming over. And we took this idea further and analyzed stream flow, observed stream flow, and looked at many different signatures, not just the recession, but many different signatures of the stream flow, like the flow duration curve, or the flood frequency curve, or the regime curve, which is the seasonal variation of runoff, or the interannual variability. All of these signatures, which are drawn, extracted from the observed stream flow data, we analyzed them separately. And then we found a way to develop new models on the basis of our understanding. So this was a systematic approach to building models. I call the top-down approach to modeling. So the idea is that you start with annual or interannual variability of flows, and you start with very simple models, simple bucket models. Like you see in this picture on the left-hand side, the S1 model, very simple overflow bucket model. And you apply that model and see how far you can go with this model to mimic interannual variability of flows. And then after you do that, you come down to the next time scale, which is the seasonal or monthly variability. And you often find that the model has to become a little bit more complex to deal with this variability. So the model has to become more complex. And you keep going down, smaller and smaller time scales, and the model becomes more and more complex. And eventually you come up with a more complex model that's appropriate to the hydrology of that particular catchment. So going from S1 to S2 to S3, S4, and so on. So with this model. So we found as a result of this that models become more complex as you reduce the time scale. And models are also more complex as you go from wet catchments to dry catchments. That was the conclusion of this top-down modeling approach. So as opposed to the upward approach or the bottom up, so you just heard from me another way of building models, which is the bottom up, which is the downward approach, or the top down approach, which is based on data-based learning. So these two alternative approaches that we came up with, obviously, they don't exactly match what you come up with from the bottom up. and what you come from the top down, they don't exactly match because we still have a lot more understanding still to develop. So we still haven't completely bridged the gap. So this top-down approach to modeling that I presented to you emphasized to me more than ever before that instead of, in addition to focusing on space scales, spatial variability and heterogeneity, we also need to look at temporal variability. Hydrology catchment behavior is also organized. The variability is organized along time scales as well. So you're talking about interannual, seasonal, daily, and so on. So catchments then organize themselves, catchment correspond to organize itself around these variabilities. So this is an idea that came out from the top-down approach to modeling. And so I was, in fact, heavily influenced in this case by a master student of mine. I just want to give credit to Justin Robinson, who did a lot of the early thinking for me, helped me in my development. So he helped me with the idea that the time scales in the climate and the time scales associated with catchment, they interact together. And what you see in observed runoff variability is actually an emergent behavior that results from these interaction between time scales. And he took this idea further, and the idea that the interaction between time scales also manifests in space scales. That sometimes some of the scaling behavior that you see in nature, for example, in this picture I'm presenting to you the variation of annual maximum flood peak as a function of catchment area. This is an important scaling behavior, and people have applied fractal methods to characterize this variability, that this relationship is fractal. But Justin Robinson did very simple-minded analysis to show that this otherwise simple fractal behavior with a negative slope of minus 0.3 comes about as a result of complex interactions between timescales. That was a magnificent insight that his work introduced to me, and that another insight that he introduced to me was that otherwise complex phenomena can be explained using simple models. That even simple models can explain, simple models that are based on interaction between timescales can explain complex phenomena. So I just wanted to show you this slide that this was a development that I came to, that in addition to mimicking observed hydrographs as a way of estimation, I think this led me into a new way of thinking, that in addition to estimation, I think we should also use the data as a way of understanding. So from estimation to explanation. That was a transformation in my thinking. And I want to now present to you some work that I subsequently did as a continuation of the top-down approach. So I had a student from Thailand. I asked him to analyze stream flow variability, especially interannual variability, over many catchments in Australia and New Zealand. And as a way of understanding the differences between catchments. So again, let me say that we were interested in the differences between catchments in respect of interannual, in other words, between year variability of runoff. And we wanted to understand what aspects of climate, what aspects of especially rainfall variability has an impact on this interannual variability of runoff. So he built some models, top-down, based on top-down approach, and then played God with the models. He, instead of changing the parameters of the model, he played with the inputs to the catchment, rainfall inputs, different kinds of rainfall inputs. And to cut the story short, I just want to state it very simply. What we found was that the interannual variability of runoff was impacted by not only the interannual variability of rainfall, which is obvious, but also some aspect of the within year variability, whether it's storminess or seasonality. And they also had an impact on the interannual variability. And depending on where you are, different aspects of variability, rainfall variability had an impact. For example, in Western Australia, where I came from, the seasonality was the factor that contributed to much of the inter-annual variability. If I'm in Queensland, in northeastern Australia, it was storminess that had an impact on the inter-annual variability. So that was a profound conclusion that came out of this work. But more importantly, this also led me into another way of analyzing catchment understanding, gaining understanding, which is comparative hydrology. That instead of studying one catchment in more and more depth, you actually start studying catchments in comparison across climates, across geographical regions. So, and look at similarity and differences. I just want to present this picture to you. This was work done by geographers in Switzerland, and they came to somewhat similar conclusions that if you are able to characterize catchments in terms of what we call Chernow phases, that across a transect in Switzerland, you can see catchments are actually different in different parts of the catchment, because the climate and the landscape had an impact on runoff in different ways. Okay, so I just want to finish this idea with this conclusion that that I learned from my analysis of comparative hydrology, which is that just like human beings, catchments are also marching. Every catchment is marching to a different drama. So I think because they have been in this place for a long time, so they're responding and adapting themselves to the climate variability. And what you see is a result of millions of years of coevolution or adaptation of these catchments to the climate variability. Okay, so this led me to this idea of timescale interactions and the idea of catchments as complex systems, complex adaptive systems. So the usual way is to treat the catchment as a simple system. You have the catchment, you have the rainfall goes through the catchment and it produces a transformation, you get the runoff. But in reality, catchments are much complex systems. They have lots of contributing parts. You have the landscape, you have the soils, you have the vegetation, you have the river channels. They are all different components of the system. They are all interacting with each other, and they produce complex outcomes. So I think that is something that came through from analysis of catchments in different parts of the world, or different parts of Australia and New Zealand. It's complex adaptive system. So this led me to the idea of catchment coevolution and emergent dynamics. So you have scale interactions over multiple time scales, and then you have interaction between different systems, and you have fast systems and slow systems interacting together, and the result is coevolution and emergent dynamics, emergent patterns. So that is a particular perspective that came through from the analysis that we did. Okay, so this comparative hydrology eventually led to an idea that different parts of the world, wherever you have catchments, they have evolved over time, depending on the local conditions, and if, in addition to the traditional Newtonian approach, building up from the bottom, that we have to look at these catchments that have co-evolved. So that introduced me to the idea of the Darwinian approach to understanding that all these catchments have co-evolved over millions of years. And so what you see now is a result of this coevolution. So that history of coevolution, that the history matters to the similarities and differences between different parts of the world. So this is the new way from the Newtonian approach that we are very familiar with. And so this was work done by a Dutch visiting student, Wouter Berghaus. He came and worked with me for a few months and built models of hundreds of catchments across the United States and looked at the similarity of runoff behavior and he classified the catchments into different groups, and these are the different colors, and he tried to understand the contributing factors that contributed to the classification or the similarity and differences of the catchments. That is interesting by itself, but what was more interesting to me was when he overlaid these classes of catchments on the landscape, on vegetation classes and soil orders and so on. He found some very close association between the similarity of water balance behavior and similarity of soil patterns or vegetation patterns and so on. So confirming the idea that landscapes, catchments have co-evolved, that we need to look at all of these things together. So the idea of the Budyko curve is very familiar to Russian scientists. So even on the Budyko curve, for example, here you present the evaporation ratio as a function of the aridity index. These different classes of catchments organize themselves different places on this graph. So the Budyko curve itself is a manifestation of catchment coevolution. So this is an example of how catchments organize themselves that is not captured in the Newtonian approach. So we definitely need the Darwinian approach to develop our understanding of how catchment behave, how catchment respond to rainfall inputs. So let me just, I'm coming to the last part of my talk. So let me just take you a little bit, take a step back. Now, this paper by James Duke was published around the time that I was finishing my PhD. So it was a paper that had a huge impact on my thinking. And, you know, it's one of the papers that I read almost every week for inspiration, even now. I mean, because there's so much information packed into this. And it was called Looking for Hydrologic Laws. And Duke focused on the importance of scale, the parameterization of microscale effects, dimension analysis and similarity, and searching for laws at the macroscale. All of that I covered already in this lecture today. But one of the things that Jim Duke missed out, he was heavily focused on, I would say, the Newtonian approach still. But I think that what I have learned subsequently after my PhD was that these need to be balanced. The Duke approach has to be balanced by the Darwinian approach. But that was the missing thing. That was what we have gained in understanding over the last 25 years. So, and if we want to make progress from now on, we definitely need the Newtonian approach, but we also need to learn from the Darwinian approach, and we need some kind of a synthesis. So the Newtonian approach and the Darwinian approach, this is a figure taken out of the book published by Günter Blöschel, edited by Günter Blöschel, that you have Newtonian approach gives you local understanding because it's a bottom-up approach. The Darwinian approach gives you more generalized understanding because it draws lessons from comparative studies across many parts of the world, and then you find a way to bring them together. That synthesis needs to happen. We still haven't made progress in this area, but progress in hydrology needs a Newtonian Darwinian synthesis. We just keep this slide. Yeah, let me just show you first that I think we have, I believe I have 5 more minutes, I'm not sure.
Yes, 7 minutes, sure. Yes.
Yeah, that's right. So I just, through this the Budyko curve idea here, just to give you the idea that catchments are co-evolved, my colleague in Delft, Hubert Savenay, did some interesting work on the same catchments that Walter Berghaus did, and one of the things that he found out of the study is confirming what we learned, and one of the things that I want to confirm is that in their study they found that the vegetation evolved in such a way in these different parts of the United States. The depth of soils was consistent with the depth of plant roots, and which is connected to seasonality. So in other words, climate especially climate seasonality, had an impact on vegetation in the way that they adapted themselves, and so he found an analogy between what the trees did, how they adapted to the local climate, to what people do, like building storages. So developing deep roots is a way of enabling them to store more water. So this is an interesting confirmation and concept that Hubert Savonai came up with, and finding an analogy between what people do and what trees do. And Robert Horton, the father of American hydrology, had this idea already back in 1933, that natural vegetation of a region tends to develop to such an extent that it can utilize the largest possible proportion of the available soil moisture supplied by infiltration. So trees do this already, but unfortunately we did not build on this understanding that Robert Horton already had, because we went down the Newtonian approach for a long period of time. But I think we can now balance it. So, so there's a lot more work that needs to be done, looking at the role of vegetation, and especially the idea of how vegetation, trees maximize, adapt themselves to the environment. And this is a work that done by my former student Stan Szymanski. He called it vegetational optimality, that what they know, the main business of trees is photosynthesis, and what they do, what they do is try to maximize net carbon profit, and the evaporation is a essential byproduct of that. And so that idea is one possible idea that we can use to bring the Newtonian and the Darwinian approach together. And we can go even further and take it one step higher and connect the optimality, vegetation optimality, to thermodynamic optimality. Now, in the interest of time, I will not dwell on this now. I'll skip this slide, but you can read about it in the paper that I circulated. So let me just skip a few slides. I had this slide before in the context of natural catchments, but the same idea can be extended to timescale interactions and co-evolution of not vegetation and water, but humans and water. We can also do the same kind of analysis, and that leads me into the idea of social hydrology, eco-hydrology. Now, social hydrology, again, in the interest of time, I will skip these slides, but we came up with a Buriko curve. We call it the social Buriko curve, applied to human extraction of water, human water. I will skip this, and also applied the thermodynamic optimality idea to try to understand the social Buriko curve. So, I'm coming to my last slide. So I mentioned to you about the Newtonian approach and the Darwinian approach. And to my mind, I think that the next major progress in hydrology, in the interest, not only in the interest of science, but also in the interest of practice, is extending the scales of interest to hydrologists to much larger scales. I call it regional process hydrology and long time scales. So this is a picture taken out of Western China. And so you look at the hydrology, the water balance of a large region, and how all these time scales and space scales come together. So it is in this context I bring up Alfred Wegener, that when you look at large regional scales and long time scales, once again, you look for emergent patterns, just like Alfred Wegener found interesting patterns, which will give you the inspiration to find connections, and as a way of building new understanding and new theories of hydrology. So that is, in my opinion, where the future of hydrology could be, going from Newton to Darwin to now Wegener, when you go to larger space scales and longer time scales. So my talk is philosophical. So again, I come back to this famous quote by Jacob Bronowski, which has inspired me for a long, long time, that all science is a search for unity in hidden likenesses. The progress of science is a discovery at each step of a new order, which gives unity to what had long seemed unlike. For order does not display itself of itself. If it can be said to be there at all, it is not there for the mere looking. Order must be discovered, and in a deep sense, it must be created. What we see, as we see it, is mere disorder. So I hope that I have given you my own perspectives, my own experience in improving myself as a hydrologist, improving my understanding, and the way I look at it, and the way Newton and Darwin and Wegener looked at it is to connect the dots. That you see evidence of coevolution, you find these patterns, and you make sense of these things, and that is the way of future. So connecting the dots is how you develop understanding. So one final parting message for young people that I have learned, and is that I think as hydrologists, I think we should focus on methods. We should focus on problem solving, not be held slave to methods. So the method-oriented person is shackled. The problem-oriented person is at least reaching freely toward what is most important, willing repeatedly to put aside his or her last methods and teach himself or herself new ones. I think this has been the story of my career, and I hope that this is an important message that many people can take on board. So that's all that I have to say. I hope that I made some sense. I hope I presented to you some ideas of how I have evolved in my own career, and I hope that I know that there's a lot more we can learn, a lot more to learn, a lot more to do. So I hope that you find some inspiration in my own development. Thank you very much, and I'll be happy to answer any questions.
Professor Sivapalan, we're applauding your lecture. Really wonderful, amazing. You presented such an interesting connection between different things. So we have, however, a number of questions from the audience.
Should I stop sharing now? Or
yes, please. If you would stop sharing the screen, then we can see you in full screen. Okay. That's wonderful. So first question is from Nikolai Yashinsky from Russia. Professor Sivapalan, do water quality models have the same scale factors like climatic or catchment time in terms of creating models from simple to sophisticated scheme, or chemistry adds scales? What is your opinion?
A very good question. I think people have already started thinking along these lines. Yes, absolutely, you are right. I think there will be similar scale-related issues in water quality problems as well. Because I just give you an example. When it comes to water quality, you have, let's say, chemical reactions chemistry interacting with physics. Chemical reaction, they have their own time scale, for example. So and the interaction between chemical timescales and physical timescales, they then can produce patterns in space and in time, and so that is definitely something that we can expect to see. I have actually done some work along those lines myself, dealing with nutrients. But the only problem for this in terms of top-down modeling is that we don't have the same kind of data that we have for runoff. So it requires a lot more data collection. So we need a large amount of data before we can begin to analyze the data properly. But I think the work has already started along these lines. Yes, absolutely right. That's a very good question.
Thank you very much. Next question comes from Dr. Pelageya Belikova of Institute for Water Problems in Moscow. Can Boudico curve method be used to characterize changes in water balance under the climate change impact?
Well, again, good question. People are already doing this. People are extending the Boudico framework to deal with not only long time scale, but also shorter time scales, but also change. So this is already happening. But the only qualification is that my understanding is that the Boudica curve comes about because of long-term adaptation. So it requires long-term for the system to evolve to reach an equilibrium. And over short time scales, when you're talking about change, you don't have enough data for the system to go from one equilibrium to another equilibrium during the transition state. And I have some doubts about whether we can actually fully address that transition period. But people are already doing that. Even recently I published a paper in Water Resource Research where the Boudica curves seem to work even at the interannual scale with some limited extent, but it does seem to work. So there's a prospect that we can still extend the Boudica idea to deal with change as well, with some caveats.
Right. Thank you very much. Another question from Dr. Belякova. There is now a lot of attention to flash floods. How does this research deepen understanding of hydrological processes?
Flash floods. Okay. Now I think I don't know that what I presented to you can address the flash flood. Flash flood is a local problem as a result of heavy rainfall. So what comes into play there is once again interactions between small time scales in the rainfall and small time scales in the catchment behavior. So in other words, when you talk about flash floods, the rainfall variability that matters is much shorter time variability. So you have rainfall variability over very short time scales, minutes, that can have a huge impact on the flood. So the scaling idea does work because it focuses you on very small time scales. So the idea of scale does matter, but you're talking about much more emphasis on small time scale variability of rainfall, for example. And then runoff generation processes that respond to high intensity rainfall. So land use effects, land use change, this kind of thing may have an impact on flash flooding.
Right. There are two questions now. One from about linking Newtonian and Darwinian approaches. So one comes from Dr. Lyudmila Lebedeva. In theory, does universal model or models of everything exist at crossing the Newtonian and Darwinian approaches?
That's a very, very good question. When we started the PUB initiative, 2002, one school of thought was that we will actually build a universal model. That one model will work for the entire world. I think that we quickly abandoned that. And I think the current thinking is that, although this is my view, that hydrology is highly local. And I think that we need to model, there needs to be a plurality of models that we need for more practical applications. But obviously you don't tell that to climate scientists, the people hydrologists who work with climate models. So we have to build global models. They build one model for the whole world because they have no option of building many different models and connect them to climate models. So they go for the universal model, but that also explains why we have a lot of trouble with a lot of the predictions by climate models, because they put just one model for the whole world and they don't capture the local complexities of hydrology in different places. So that debate is still on. I think you will have hydrologists argue for one or the other. I personally, for now, I think that we are not there yet. We don't have a universal model that can handle the whole entire world. I think we need to learn a lot more, and that's interesting research.
Right. Thank you very much. And related question, I'm misusing my my position as a moderator and also posing a question related to this. Darwinian approach, as you said, is more about finding similarities. And as you also quoted another philosopher, that we're looking for similarities when we do science. And machine learning is very good at that, isn't it? So it may find similarities between different types of catchments, atmospheric patterns, and such like. So maybe you could think of Newtonian models and Darwinian models and machine learning thing on top of it that would somehow coordinate these links by analyzing big data and past data, trying to connect these models. Would it be also interesting to do?
I think it'll be interesting to do. I mean, I have, yeah, absolutely. But my warning or my concern is that machine learning is fine, but like I said in my last quote, machine learning is a method. I think that we should not, hydrologists should mortgage our minds to machine learning. We should use it as a tool. We should not fall slave to it. Yeah, you can use the machine learning and then, but we have to bring the human mind into it.
Sure,
I think we need to learn. Yeah, I will not mortgage my mind to the a technique. I will use it, but it has to come from my head. I think that's an important distinction I make. So we have a lot of tools that we can use for understanding patterns. Machine learning is one of them, absolutely. But I would caution that, because there's a danger if somebody is listening from India, or sometimes people go for these jazzy things. Okay, machine learning will do it for me. I don't have to do any thinking.
As you know, there is a last couple of years a debate if hydrology has done enough to improve the models, and perhaps it's a time to switch to machine learning, deep learning, and such like that would do better. So this debate is going on. There are interesting papers of Wegener and Bavin answered in HP. So maybe for the audience also would be interesting to check that Wegener's paper.
I will, let me say that I'm 67 years old, so I think that people will qualify me as old-fashioned or old in my thinking, and I understand young people that, but I go back to Bronowski. I think.
Okay, so this discussion may take place maybe later during our virtual drinks. I would move to. Okay, actually, we exhausted the list of questions because we answered about data-driven models already from Fatman Wasser with a similar question. So, colleagues, then what can I say? I would like again to thank Professor Sivapalan for this wonderful exposure of not only to hydrological approaches, but also the way his thinking, his understanding was developing in time. That's really fascinating. Thank you very much again, Professor Sivapalan. So it's thought-provoking lecture, and it was great to have it as the last lecture in this school, but for sure not the least. Vice versa, it brings up, the cherry on the cake, philosophical cherry on our cake of hydrology. Thank you very much, Professor Sivapalan.
Thank you very much for this opportunity.
And again, thank you for connecting at this early hour. By the way, your papers, I asked to upload them to the website. They would be next to the link to your presentation for those who want to download. But of course, they're in open access, if I understand. One is HES, another one is...
HES is open access, but WRR not.
WRR maybe not. Okay, good. So, colleagues, we came to the end of this school, actually.